Hey everyone, this is another question for Sean. So, Sean, this time
Yes.
the scenario is like this. Um, so you have uh, we're this is during the apocalypse, and the world queen has decreed that uh, all families must have at least or must have only one girl to stop overpopulation.
Okay.
So what happens is these families will keep having children. So if they have boys, they will keep having children. If they have a girl, then they will immediately stop.
Okay.
So, given that there are uh, n families from the start,
hmm
what's the boy to girl ratio um, by the end of, or in the future, I should say.
What is the boy girl ratio
Yeah,
when every family has a girl?
yeah.
Boy girl ratio. Okay. Let's see. So I guess this is a probability question. Mm, there's n families, so the chance of having either a boy and a girl, chance
Mm-hmm.
is one half, right?
Mm-hmm.
Um, okay. So let's see. I'm gonna write some examples,
Mm-hmm.
so maybe that will paint a picture. So let's say n equals to 1.
Mm-hmm.
Chance of having a boy or girl.
Actually, let's start with a bigger
Let's
example. One,
yeah,
like,
yeah. So
yeah,
like theoretically,
yeah, 10.
10.
Yeah, that's fine. And then,
So,
so
oh man.
if each of the families were to have children, and the chance of them having either a boy or a girl is equal, then what's the expected
Mhm.
outcome at the end of this round?
Right. So for the first round,
Yeah.
you have if it's a boy,
Mm-hmm.
boy and girl, you stop.
Mm-hmm.
For the second round, this boy and girl. Hmm, interesting. So a family can have keep having boys.
Mm-hmm.
Boy. Oops.
You probably don't want to draw everything out, but like, is
I'll
there?
do it. So if the person had a girl in round 10, that means it is 9-1 for the ratio.
Mm-hmm.
So let's say.
Wait, but why is it? So you're saying if there was if one family had a girl and all of them had boys, right? But is that likely, given that the chance of uh, having both? Yeah. So what's the likeliest outcome?
Oh, okay. So for round 1,
Mm-hmm.
there'll be 5 boys.
Yeah.
And 5 girls.
Uh-huh.
I guess like round. Yeah, I guess I represent this graph. So 5 boys.
Mm-hmm. And then
say round 2.
Mm-hmm.
Be like 2.5 boys. 2. Let's just do theoretical now.
Yep.
Girls.
Mm-hmm.
Round 3 would be 3.25.
Mm-hmm.
About 1.8.
Mm-hmm.
Round 4. Well, you can't have like
Yeah.
0.75 boys. So maybe it ends at round 3. Or ends at round 4.
Mm-hmm.
Does it?
Well, if the families, well, they have to stop having children once they have a girl, right? So.
Right, okay. Yeah, so the question is how many rounds, right?
Or no, so what's the ratio? Yeah, of boys to girls when they all stop.
Got it. So can we assume that once the number becomes less than 1, for a very big number,
Mm-hmm.
you can round to a girl has appeared?
Sure, yeah.
Is that a fair assessment to make?
Yeah. Well, because I mean, it's even though the chances are equal, you can't have 0.5 of a
Right.
child, right? So
Okay,
I mean, it would either be one or the other. Yeah.
Value is less than 1. We have a girl.
Okay.
Okay, so in this case, n equals to 10. So I'm going to sum them up.
Mm-hmm.
I will assume round 4 is just 1 girl.
Yeah.
So like about 1 girl.
Okay.
We have 5. Oh man. 7.5. 8.75. Actually, what if I added this just to my calculations?
Mm-hmm.
So, 7.5, 8.75. That's 9.5. So 5 boys.
Okay.
And then 5, 7.5. I guess it's the same.
Mm-hmm.
Girls.
So can you generalize or can you explain what's going on here? How come? So
Yeah.
how
So
come? Yeah, explain why that
yeah.
policy didn't work.
Okay. Yeah. Um. So the reason why it's equal is because families that have a girl will stop having kids.
Mm-hmm.
So having a girl guarantees there's no more boys for that family.
Mm-hmm.
So for each additional girl, you have theoretically a family that keeps having one more boy, another family that keeps having one more boy if the last one was a boy.
Mm.
Um,
But how come? So each family only has one girl, right? But then some families have more than one boy. So how come the ratio is still the same?
um,
I mean, it's right. I just want you to explain it.
let me complete this graph.
Okay.
That may help you answer this question.
I think a better way uh, to do this is so maybe like how I would represent it would be to use a outcome tree.
This part.
Yeah. Or I mean like a tree basically, a sideways binary tree.
Let's see. Well, I think I can explain by just looking at this. So, like, round one makes sense because the possibility of having a boy or girl is half.
Mm-hmm.
Um, if you so now you've taken all the families. So since each time the probability of having a boy or a girl is half,
Yeah.
even for the people who kept uh, giving birth because of the boys,
Mm-hmm.
the probability is still half. Um, so in that sense, it doesn't really matter if you need to stop by having a boy or a girl.
Mm-hmm.
Um, if there was no rule to stop, it would
Mm-hmm.
still be about the same.
Okay.
Um, so
So because here you're just looking at the generations, right, and not at the
right,
at the so ignoring the number of families having children, if you look at each generation, it's about roughly the same, right? Okay. Yeah, I think that's it.
okay,
Okay. Um, let's
this is
see.
easier than I thought.
Yeah. You did well. So it's good that you clarified whether having a boy or a girl, um, whether there's an equal chance of having a boy or a girl. Because this I didn't tell you. So it's good that you didn't assume you asked. That's it.
Okay, all right. So
I'm gonna.
yeah, I think it was helpful that you told me to list out the generations here.
Mhm.
I would have done it a different way, but I think this was probably clearer.
Yeah. Okay, I'm gonna stop the stream now. So thanks everyone for joining us. Hey everyone. So this time we have another question for Sean. Um, So Sean, the question is, um, imagine a hallway with 100 closed lockers. Um, so a man first opens all of them, and then he closes every second locker. So on the third pass, he toggles every third locker. So what this means is if it's already open, he closes it. If it's closed, he opens it. And then
Okay.
on the fourth pass, he does this for every fourth locker, and so forth. And then he does it for 100 passes. So at the end, he just toggles the 100th locker. So after he does all this, how many lockers are open?
Okay. He toggles every third locker, closes it. Okay. This process continues. So, so the initial case he's working with is like, let's use 0 to represent closed,
Mm-hmm.
and then 1 to represent open. You're saying, oh, this question is saying from the third to the 100th pass, it is a toggle, right?
Yeah. Well, actually, you can think of even the second pass to be a toggle, right?
That makes sense. Yeah. It closes every second. Okay.
Actually, you can
So
think of all of them as toggles if you
yeah.
start with all of them closed.
No, you're right. I guess like if he opens, if it's all initially closed. Okay. So let's just do pass 1. Pass 0 is like. So I'm just gonna do the first 10 lockers.
Okay, yeah, that's a good way of generalizing.
1, 2, 3, 4, 5, 6, 7, 8. So on the first pass, it's like 1, 2, 3. I'm gonna make this monospace.
Mm-hmm.
Oh man. Second pass closes every second locker.
Mm-hmm.
So 0, 1, 0, 1, 0. Every second. Okay, wait. So it should be 1, 0.
Mm-hmm.
The third pass closes every third locker. He toggles every third locker.
Mm-hmm.
So 1, 2, 3. 1, 2, 3.
Mm-hmm.
1, 2, 3. Is that correct? This is the third. This is the third. This is the third. Okay, it seems correct. Okay. I'll just drop the 5. Okay, 1, 2, 3. 1, 2, 3. 4. 1, 2.
Mm-hmm.
1, 2, 3, 4, 5. 1, 2, 3.
So I think you made a mistake here.
1, 2, 3. 5, 1, 2, 3. Like that, right?
Okay, yep.
Let's see.
Or maybe you can just. Would it help if you just copied this down to the next line?
Sure. Do it to 10.
I think 10 is a good sample size. I mean, like, copy it each time so that you don't have to.
Oh, I see. 1, 2, 3, 4, 5, 6. One, 2, 3, 4, 5, 6, 7. Two, 3, 4, 6, 7, 8.
Okay, so I think you also made a mistake earlier on.
Yeah. Okay, this is right. 1, 2, 3. 1, 2, 3. 1, 2. Oh, this is a 0. 1, 2, 3. 3. 2, 3. Okay. 1, 2, 3, 4. 2, 3, 4. 2, 2, 3, 4. 2, 3, 4. 1, 2, 3, 4, 5, 6. 2, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay. 1, 2. So this is toggling. This is toggling. This is toggling. This is. So this is a 0. It's a 0.
Mhm. This So I
toggling.
think
This is what
let's
correct?
see. Well, the tenth pass is incorrect. Yep. So now it's correct. So
Alright.
is there any pattern you can see?
Yep. Let's see.
So which lockers are open at this point?
Locker 1,
Mm-hmm.
2, 3, 4. 1, 4, and 9.
Mm-hmm. No, you don't have to do that. I mean, at this point. So, um,
So I guess like as we go up in numbers,
mhm.
you toggle less and less.
Yeah. So
So you already know for sure. Like at round 10, you know these aren't going to change
Mhm.
because the higher you go, you'll just kind of skip these.
But okay, I want to ask, uh, why those lockers specifically? Why are they open? Like, what distinguishes them from other lockers that are closed?
They are things that distinguishes them. Well, first of all, they are not prime. Um, they are square roots of each other, of 1, 2, 3. Um, that might be something.
You're very close, but
Earth squares.
mm-hmm. So what? Why would them being squares affect whether they're open or not?
Um, okay, so for 2,
Mm-hmm.
uh, give me a second.
Okay, so
Wait, give me a second. I think I can figure this out. So the fact that they're still open means that they've been toggled an odd amount of times,
mm-hmm.
or rather, even amount of times in this case. Does that matter? 2, 3, 4, 5, 6, 7, 8.
An odd amount of times, right? You mean?
Uh,
Because you're starting with them all closed.
right. Okay. Yeah.
So for let's say locker 4, when is it toggled? On which
Locker
passes?
4 is
Yeah,
toggled on 2,
on which passes?
2 and 4. Locker 9.
And also 1, right?
1, 2, and 4.
Mm-hmm.
Yep. So they are divisors of 4.
Mm-hmm.
So each locker will be toggled by any of its divisors.
Uh-huh.
And 9 in this case has a divisor of 1, 3, and 9.
Mm-hmm.
Which is 3 times. But if you take 8, it's 1, 2, 4, 8, which is 4 times, which is even.
Mm-hmm. So what?
4 is 1, 2, 4. So for a odd amount of divisors in a given number, it will be open.
Okay.
For that number.
Mm-hmm. So when does it have an even number of divisors, and when does it have an odd number of divisors? Can you generalize?
So it'll have an even amount of divisors because the divisor takes two values. It will be odd when the two values are the same.
Mm-hmm.
meaning the square, they have a perfect square root,
Okay. So.
or else it's going to be.
Mhm. Okay. So, let's go back to the question. So there
Okay.
are 100 lockers. So after 100 passes,
Mhm.
how many are going to be open?
Okay, so after 100 passes, we want to find all the perfect squares below 100. So, um, perfect square roots, not just perfect squares,
Perfect squares.
below 100. So I can just list it out. It's 1 squared, 2 squared is 3, or sorry, 2 squared is 4, 3 squared is 9. Let's just do the amounts. So 3, 4, 5.
Yeah.
25. 6 is 64. Sorry, 36.
Or you could just say 6 squared.
49. 8 is 64. 9 is 81.
Mhm.
And 10 is 100.
Mm-hmm.
So we have 10 loggers that are open according to this.
Yep, that's correct.
Okay.
Yep.
This is a neat problem.
So, what you did well was you picked a small enough example size, but it wasn't like too small. So I don't know if you
I was gonna do up to 5.
did that by chance, but if you just did up to 5, I don't think you would have been able to see.
Yeah, I don't think I would have seen the pattern.
See the pattern. So, yep. Yeah, that's it.
Sweet. Cool.
Okay.
I like this question.
I guess an easier, so like what you did was okay, using ones and zeros. I think what might have made it easier to see would be to, well, you can't do it here, but like on paper, if you just
like dashes and like O's.
if you just mark it every time, then it's then you won't make mistakes copying them over, right? So
Yeah.
yeah, but that's just one little thought I had. So
Yeah.
yep, that's it for this question. Thanks for joining us, everyone. Hey everyone, thanks for joining us again. This time it's my turn. Sean has a question for me.
Alright. So it's called smallest difference.
Mm-hmm.
Given 2 arrays of integers, do the pair of values, one from each array, with the smallest non-negative difference, and return the difference.
So let me make sure I understand that. So I'm given 2 arrays of different sizes, right?
They can be different sizes.
Okay, so let's say they're different sizes of non. Did you say negative and non-negative integers?
Both, yeah.
Both. Okay, so and I have to return the smallest difference between
any values from each of them.
So, for example, I could have let's see.
So I'll give you an example here.
Mm-hmm.
This is only positive numbers. So your input is array 1 is 1. 1, 3. 15.
1, 3, 15.
11. 2. That's it for that one. And the second array is 23. We might need a bigger cell here. 127,
Mm-hmm.
235, 19,
Mm-hmm.
and 8.
Okay.
So, and your answer should be 11 and 8.
11 and 8.
Well, your output should be 3, which is the difference between 11 and 8.
Smallest difference. So I also want to ask if the two values have to be from the two different arrays. So, okay, I guess it does. It can't be like 3 and 2.
No, it's from different arrays.
Okay. So I guess a brute force way to do it would be to step through each element of the first array, and then for each element go through the second array and compare their difference, and just remember the smallest difference. But then,
let's assume our input is all positive.
I would just I just need to look at the difference as in the absolute value of one of these subtracting the others. So I wouldn't have,
Yep. Okay, that works.
Yeah, so that would just give me so even if it was like say 1 minus 19, that would give me with 18. I would just find the absolute value of that to get me 18. So if I did that, it would run in O(n) squared time. I want to optimize it so there. Should I try to optimize it?
Sure.
Okay, so these arrays, I'm going to assume that they're not sorted.
No, do not.
Okay. Would it help if they were sorted?
You can try it.
Okay, assuming if I have so that sounded like no, that's not the solution I'm looking for, but I'll try it anyway. So let's say we have 1, 4, 5, 7, 20, 35. And the second one we have so actually I'm going to remove this. 1, sorry, so
do like really big numbers and help maybe. Or use the one from the example.
Well, if they were sorted, then it would be, I would have 1, 3, 5, 11, 15, 8, 19, 23, 127, and 235. If I were to step through them at the same time, if they were sorted, perhaps I could merge them together. So to merge them, I guess this would take A plus B, because I would just be looking at.
What do you mean by merging them together?
If I merge them, I would get it. If these two are in sorted order, I would merge them, and I would get 1, 2, 3, 8, 11, 15, 19, and so forth. And then I could just look at the difference between each number. And
the problem with that is you don't know which array they're from, right?
Right, yeah. Okay, so it wouldn't. And I don't think I want to use additional space to know where they're from. And I think that would unnecessarily complicate the problem. So
go back with their sorted arrays.
Okay, so
sorry, I should have stopped you.
It's fine. Okay, if I have okay, well, if one number here in this case, if I was looking at 1, and I compare it to 8, I probably know that I don't need to compare it to 19, because the difference would be even greater.
Right.
And that's true because 1 is smaller than 8. If I was looking at 15 and 8, I would probably still want to move on, because the difference between, say, 8 and 9, sorry, the difference between 8 and 15 and 9 and 15 is actually smaller. And in this case, the first number is larger than the second number. So maybe I can generalize this. If so these are, let's say these are n1 and these are n2. I'm just gonna, so for each n1, for each n1, if n1 is smaller than n2, then we just look at the first one, and then if it's, we just remember the difference between, diff of n1 and n2. If it's not, if n1 is actually bigger than n2, we keep doing this. So while n1 is bigger than n2. So I'm going to check later to see if it should be. Can there be duplicate elements?
Yes. Yeah. Well, duplicate elements.
Let's say there's 15.
It wouldn't change your output, right? So.
Well, wouldn't it be 0 then? The output.
Oh, you mean between the two
Let's
arrays?
Say, yeah, there's a 15 here.
Yes, there can be.
Okay, and that in that case the output should be 0.
Right.
Yeah. So if it's so, let's say in this case 15 is greater than 8. 15. So we move to the next one. So remember the diff of n1 and n2, and then just go to next n2. In the worst case, this would probably still be O(n) squared. So here, for example, let's say if we're looking at 11, we would look at 11. Okay, actually, let's start from the top. Should I try to? Am I on the right track, or should I try to come up with a different?
I think on the right track. Try walking through an actual example with your logic.
Okay, so let's start at 1. So n1 is 1. If n1 is smaller than n2, it's smaller, yes. So their difference is, okay, so actually I want to say, when I say remember diff, I'm actually recording.
Mm-hmm.
So record smallest. So record min diff.
Yep.
Okay. So the difference is 7.
Mm-hmm.
And so now I'm moving on to next n1. n2, so n1 to 2 is smaller than 8, and their diff is 6. So it's
Mm-hmm.
smaller, so I'll replace this. And then n1 is now 3. 3 is smaller than 8. Their difference is 5.
Mm-hmm.
Now it's 11. Okay, so now we have a special case. 11 is actually greater than 8. So while this is greater than 8, get the minimum difference. So 11 minus 8 is 3. Yeah, that's smaller. And then let's go to the next n2. So now n2 is 19. 19, 11, and 19, their difference is 8. So 11 and 19. 11 is actually smaller than 19. So we just record the minimum difference, and we actually skip to the next n1 because that condition is, yeah. So actually, I guess I should have. I might have missed a. So maybe there needs to be another check at the end here. Yeah. Yeah. So check again after. Okay. So now this is 15, and 1 is 15. Do we need to start from the beginning or not? Uh, we don't. Oh, we don't need to start from. Okay, this. I'm inclined to say we don't have to start again from 8, because we know that if if
Why not?
we already compared 11 and 8 before,
Okay.
and so and and we moved to the next number, right? Because 11 was greater than 8, and now 15 is greater than 11. So we can only get a larger difference if we compare these two.
Okay.
So we actually don't have to move back. So here we're comparing 15 and 19, and their difference is 4, which doesn't beat 3. And so we're done with n1, and our result, our difference, our smallest difference is 3, which is consistent with what we expected. So the runtime for this the worst case runtime would be so if they were all small, if all n1 elements were smaller than n2 elements, then the runtime would just be O of n1. If they're all larger, then it might be O of n1 plus n2. Because you don't go back, right? So basically, because you don't really reset the pointer of n2.
Okay.
Yeah, so actually you're just stepping through both arrays.
Yeah.
Okay, so
yep.
Should I?
So that is the efficiency for a sorted array.
To sort the array,
your raw input was unsorted.
So to sort the array, it would require n log n time. So the runtime for doing this is n. Okay, so I guess it would be n. So, sorry, I'm going to use a and b instead. A log a plus b log b, and we can actually simplify this to assuming n is the longer array, the length of the longer array. We can just say this is O n log n. Plus, once we've sorted it, we step through both of them. In the worst case, well, it would still be n, because in the worst case, it would be 2n, so it would still be n. And actually, we can remove this slower increasing term, less significant term to get O n log n. Is that correct?
Keep it at the two variables for now.
Okay.
I think that's acceptable, right?
So in that case, it would be
Yeah, so just a log a plus b log
and yeah,
b.
plus a and b, but then those aren't significant enough. Does that make sense? It would be like this.
Here in the answer it says overall runtime is a log a plus b log b.
Mm-hmm.
I think they condense the
Because I think
constants into
because if you have a log a and then you have a, then the second a
it's like two a log a, right?
yeah, it doesn't. I mean, it's
Yeah, so you don't need those.
Yeah, not significant anymore.
Okay, let's jump into implementation.
Okay. So
assume you have a sort method already.
Should I use Atom instead?
Hmm? Oh, sure.
Yeah, it might be.
Yeah, I'm not. I'll follow on your string. So, should be fine.
So I'm given two arrays, and I want to find their smallest difference of two integer arrays. Is that yes? Return so. So I want to set this to max value. I think that's what it's called, and then modify it as I go along. So if let's look at what I had before. So here I'm looking through each. So for each integer n1 in A. So here are two conditions. If n1 is smaller than n2, then so min diff equals is the min diff smaller than their difference? If it is, then keep min diff. Otherwise, sorry. So is it smaller? If it is, keep it. Otherwise, replace it with new diff. Okay. Else if n1 is greater or equal to n2, so this includes cases where if n1 and n2 are the same. Actually, I think I could also do it here instead. Yeah, we'll check later when we run through the example. So so while n1 is greater than while n1 is greater than n2, right? So I need to define what n2 is. While n1 is greater than n2, we want to n2 would be the next element in B, and so we get the difference again. And then okay, and then
okay, I'm gonna say you can do everything in one while loop.
Okay.
But keep track of your indices outside of the while loop. I guess like instantiate your indices outside of the while loop.
You mean this, right? Or I guess that wasn't what you were talking about, but yeah. So
you're iterating through two arrays, right?
Mm-hmm.
The arrays are never going to go
so instead of doing this, I should.
Mm-hmm.
Yep,
I think the for each kind of method is kind of screwing you over because in for each you don't keep track of index.
Okay, so so the index of A and the index of B. So while index of A is less than A dot length, so while it's less than A dot length, we compare if n1, sorry, so if A, so this is essentially A1, n1. N1 is less than or less. Okay, I guess I have to check later. Less than or equal to this, then report the smallest difference. Otherwise, if it's greater than the element in B, then hello? You still there?
Yep, I'm still here.
Okay. So if it's greater, then what we want to do is we want to increment so sorry, this.
No worries.
Yep. So for the in the while loop, we're like we're going through each element of A, so we would have an increment. We would increment the index of A at the end. But here in this in the case that number 1, so A1 of A, sorry, I'm just going to say N1 and N2, N1 is greater than N2, then we will get the difference again.
Mm-hmm.
And then go to the next N2. Maybe I can simplify this. Let's see. So, well, I need to check if it works first. So I'm gonna walk through it. So let's delete everything below here. Okay, so let's say A1, sorry, AI, BI, diff. Okay. So let's go back to our now. So A and B indexes are at 0. This is max. So let's look at now. Index is okay. So the first, so N1 here is 1, right? N2 is 8. And
yep.
So this is still within, this index is still within A. So if this is less than or equal to B, the index at B, sorry, the number at B, so if 1 is less than 8, yes it is, well the difference is 7. And is that 7 smaller than integer max value? Yes, so it's 7 now. Now we increment A index. Now we go back again. N1 is now 2. Is 2 smaller than 8? Yes, and their difference is 6, and that is smaller than 7. So I might skip a little here to make it faster. So 3. So AI is 2, and 1 is 3. The difference is 5, which is smaller, so I update that. Now we have something interesting. AI is 3, and N1 is 11. Here, they're not the same. Sorry, 11 is not smaller than 8. So we go to this part of the code. The new difference is 3. And we change that to 3. And B gets incremented.
Mm-hmm. What do you see wrong here? What if you flip the inputs N1 and N2? What happens?
If I flip N1 and N2?
Yeah, so let's say instead I put array A as the second parameter and array B as the first parameter in this function.
So I guess I wouldn't have to deal with more like special edge cases. You were saying instead of traversing array A, I should, if I traverse array B, I might have an easier time, right?
I'm saying the solution will break if A and B are reversed.
Okay.
So pretend n2 is n1 and n1 is n2. Every step in your while loop for the A inside that while, you'll actually increase regardless, right? So by the time you get to 15, you're already at 235 or 127.
Right. So if it was here, would that? Let's see if that would.
Okay.
So
there's one more way you can simplify this. Else a group.
I see. These two lines are the same. So let's see what would happen if I copied them out here. So I'm gonna start again.
Yeah. So try it with the arrays flipped. And see if you get the same result.
Okay. So. All right. So start off with both indices being 0. N1 is 8 and N2 is 1. Then the difference is max. Now, while the index is still valid, we get the difference between them two. So now it's 7. So if A1, if N1 is smaller than N2, it's not. So N1 is bigger than N2. So we increment B.
Okay.
Okay. Now, I feel like this might trip me up a bit, but so please, let me know if I got something. If I look at the wrong number. Okay. So now their difference is let's update N1 and N2. N1 is 19. Okay, so I see what you're saying.
Okay, so for your second iteration, you're incrementing N2. Is that correct? So BI. For the first 8 iteration, you're incrementing BI, right? Because A, which is 8,
8 is greater than
1.
Okay. So it's 2.
Right. Yep.
Okay.
That should be good.
Okay. So now their difference is so let's see. Their difference is 6, which is smaller than the current minimum difference. And now, which of these are we incrementing? We're incrementing B and 2 because 8 is greater than 2. And so now we're looking at 8 and 3. The difference is 5. And 8 is still greater than 3, so we increment b again. So now we're looking at numbers 8 and 11. Now, n1 is smaller than n2. 8 is smaller than 11. So we increment a. That's 1. So now we have 19 and 11. Their difference is 8, which is not smaller than 5, so we'll not replace it. And now, 19 is greater than 11, so we increment b. And now our numbers are 19 and 15. And their difference is 4, so I replace min diff with that. And n1 is greater than n2, so I increment.
Okay. Wait, is your min diff supposed to be 3? From 8 and 11, right? Did you update that?
Oh, yeah. Sorry. So.
Alright. You're almost there, Greg. Hang on. You're almost there.
Okay, so I forgot to. Let's see. 0 here. Sorry. A1 is 0, and N1 is 0, and N2 would be 11 at this point. So I change, I update.
Does the loop keep going after that?
So this is 3.
Okay.
And so here, N1 is smaller than N2, so I increment A, so that's 1. Now N1 is 19, so the difference is 8. I don't do anything, but instead I increment B. So now N2 is 15. Their difference is 4, and I don't change it. And here, N1 is greater than N2. 19 is greater than 15, so I increment B. And now, A1 is not within the bounds of, not a valid index of A anymore, so I stop. And now I
But A is 1 though, right? A of I is still 1.
Crap. Sorry. So I need another condition here.
Mm-hmm.
So while I'm still looking at, well, I mean, I could, yeah. So I would need a condition to let me know that I need to exit out of the loop, and that would return the minimum difference, which is 3, which is consistent with our expectations.
Okay, good. So last thing is, what is N1 in your code?
What is N1?
On line 12.
Ah, right. Let's see.
All right. Yep. So yeah. So this is the solution. The optimal solution.
Okay.
I think it's good. It was good that you actually defined min diff as integer max value, knowing that you'll start from max. I guess if you're writing that, maybe mention like, oh, well, we'll assume that the difference is the maximum difference is going to be not bigger than the x value.
Okay.
Um, yeah, I think it was good that you mentioned sorting.
Mm-hmm.
You might have discounted it a little bit too early.
Yeah. Oh, and I guess here I actually didn't implement the sorting, right? So.
Oh yeah, you didn't sort it. Yeah. No, yeah, you're right.
Okay. So maybe I should have something that says A equals sorted A, something like this.
Right. Yeah. Yep. I think in here it says it uses the arrays class.
Mm-hmm.
Arrays.sorted.
Oh, sorry.
Arrays.sort parentheses A. Yeah.
Sorry, I yeah.
Yeah, no worries. I think that's fine. Even if you did have that shortcut. Yeah. I think one thing to avoid tripping up when I told you to flip the input, maybe write N1 again on the bottom. Right, I guess write the old N1 on the bottom. Yes.
Yeah, save
so I think
like,
a little bit confused.
I was like lazy, so I guess I should have done this instead.
Yeah.
Right.
Mm-hmm.
Yeah, that would have been easy actually.
Yeah.
Okay.
Yeah, I think that's it.
Okay.
The thing with I guess if you're dealing with indexes, which you are, avoid using the for each loop because you'll have to keep track of that explicitly. I guess for each loops will work as well.
But easier to screw up, I guess.
The good thing about while loop is you're traversing two arrays. The moment you hit one of them, you can just exit. Whereas I guess a for each or a for loop through a certain length, where you might have the answer already and just keep going. Yeah, so I guess just be careful when you use which. Sometimes it's good. I think overall it went well.
Is there anything that I could have done better? I think
the coding, you were kind of caught up in a lot of nested loops. So perhaps walk through a complete example with different use cases. And maybe different inputs as well.
So don't just rely on the given input. Okay.
Right, the first example. I think so. The A dot length makes more sense in your previous implementation because they're the same length, right? But if A was only one element, you'll get an index out of bounds. Or if B was only one element, you'll get an index out of bounds. You're trying to increase B. Yeah, so I would say, do try it with multiple inputs, more than one example. But I think everything else came naturally. Oh, and don't forget that you sorted it.
Yeah.
Because, you forgot it for the Big O implementation, or the Big O calculation.
Okay.
And, that's it.
Okay. Thanks, Sean.
Yeah, no problem. Thank you.